Thanks very much, and thanks to the organisers. I had a great day yesterday, and I'm sure today will be equally enjoyable. So the topic of my talk today is going to be a question which has been on everyone's lips for the last 100 years, namely, what is special about general relativity? There's kind of a cartoon history of this question. Many of us will know it already, but for those that don't, I'll just repeat it now. So after 1915, when Einstein had constructed his general theory of relativity, he said that what made this theory interestingly different from the theories which had come before it was that it is generally covariant, that its equations, the Einstein's equations, hold in all elements of a class of coordinate systems related by smooth but otherwise arbitrary transformations. Unfortunately, it doesn't really work, this criterion of general covariance, as a way of distinguishing general relativity from the theories which had come before. So Kretschmann very quickly pointed out to Einstein that you can make any theory that you want generally covariant. Just take, for example, the Newtonian theories which had come before Einstein, just write them in an arbitrary frame. Sure, you'll get extra terms, but once I've written the theory in that way, the theory is generally covariant. So if I want to use this, or something like this criterion, as a way of distinguishing general relativity from the theories which have come before, I'm going to have to try a bit harder. Then began the project of trying to articulate a substantive sense of general covariance. And this rumbled on for the next few decades. At some point in the second half of the 20th century, the debate acquired a new name. The project became to identify this notion or quality of background independence, which general relativity was supposed to have, and which the other theories which had come before it, like Newtonian mechanics, did not have. Really, this is just an old debate under a new name, but the new branding did inspire people to do new work. And from the 1980s onwards, people articulated a lot of really interesting senses in which you might point to a property that general relativity seems to have that other theories don't have. Unfortunately, at this point, things get rather murky because everyone advanced a different notion of background independence. Moreover, no one really applied them to particular theories other than general relativity very precisely. So the first thing that I want to do in this talk is kind of try to be a bit more systematic about this. So I'm going to present to you 5 definitions of background independence from the last 30 years or so, which I think are very interesting and worth looking at. And then I'm going to apply them not just to general relativity, but to a number of other classical space-time theories as well. And we're going to find that, contrary to some of the claims which people sometimes make, none of these definitions really neatly pick out general relativity. There are a number of other theories which also satisfy these definitions of background independence. That's going to be the first half of the talk. In the second half of the talk, I'm then going to move on to quantum gravity. Another claim that one sometimes finds, especially in the writings of, for example, Carlo Rovelli and Lee Smolin, is that background independence is an important guiding tool in the construction of a quantum theory of gravity, and that certain quantum theories of gravity, in particular string theory, are not up to the task because they do not manifest this quality. Again, I would like to see a little more precision in the debates on background independence in order to figure out whether this claim is true or not. So what I'm going to do is I'm going to take these 5 definitions, I'm going to translate them to the quantum context, and then I'm going to apply them to string theory and loop quantum gravity, and I'm going to see what they say. And the conclusion is going to be that when it comes to string theory, the situation is a lot more subtle than this one-liner that string theory is not background independence might suggest. When it comes to loop quantum gravity, in fact, we do adjudicate that this theory is background independent. So I'm not really criticizing the positive claim of Rovelli and Smolin about their own theory, so much as saying that the situation when it comes to other theories like string theory is a bit more subtle. Good. Okay, so let's start off with the classical stuff. This slide is going to be boring to philosophers. It comes up all of the time, but it might be useful for physicists to see the ways that philosophers often like to think about space-time theories. So, given a theory, which we'll call T, we can say that the kinematically possible models of that theory are picked out by certain tuples of objects. So here we have M, the differentiable manifold. We then have a number of objects, F1 to Fn. These are so-called fixed fields. They're fixed identically in all kinematically possible models of the theory. So one obvious candidate would be the Minkowski metric when we're dealing with special relativity. It wouldn't really make sense to be changing that object or to be thinking that it was dynamical if we're dealing with special relativity. We just fix it. And if we start changing it, arguably we're not really doing special relativity anymore. Then we have the D1 to Dm. These are dynamical fields, fields with their own dynamical equations. Usually these will be representing matter, although not in the case of general relativity. But we might have here, for example, Klein-Gordon fields, Maxwell fields, etc., etc., etc. Okay, so the kinematically possible models pick out the kinds of objects that we're interested in. Just to give you an example, general relativity, people normally speak of the kinematically possible models, or KPMs, as being picked out by these triples M, G, phi, M the manifold, G the metric field, and phi a placeholder for whatever matter fields that you're interested in. So it might be Klein-Gordon fields, it might be Maxwell fields, whatever. Note that in fact here there are no fixed fields. All of these objects, i.e. G and phi, they're dynamical. We then talk about the dynamically possible models. These are the subset. This is the subset of kinematically possible models in which the fields that I've written down in the kinematically possible models satisfy certain dynamical equations that I'm interested in. So I might, for example, think about the dynamically possible models of general relativity. These are those kinematically possible models in which these objects, G and phi, satisfy the Einstein equations plus whatever equations for matter I'm interested in. So if this phi ends up being Maxwell fields, Einstein-Maxwell theory would be the Einstein equations along with the general relativistic versions of Maxwell's equations. So hopefully all of that's fairly straightforward. I guess just one minor comment on the kinematically possible models of GR. Sometimes people write MGT. I don't really think there's a significant difference here. I have a mild aesthetic preference for this way of putting things because T is a derived quantity. It's a function of the G and phi rather than being a fundamental object. At least that's the way I view general relativity. But I don't think much really hinges on this.
T, you mean TAB?
Yeah, TAB. Is that not what I said?
You say T. So.
Oh, sorry. Yeah, that meant TAB. Yeah. Okay. So there's the setup, the framework for thinking about space-time theories. So now before we move on to thinking about background independence, it's going to be useful to think about two different formulations of special relativity. These only differ in a trivial way, but it's going to be a way that's useful when we're adjudicating or deciding whether a definition of background independence is doing a good job, because sometimes bad definitions give different verdicts on these two versions of special relativity. So here's the first version. Kinematically possible models M, fixed Minkowski metric field eta, fixed identically in all kinematically possible models. And then we have a real scalar field phi, which satisfies this massless Klein-Gordon equation. Seems like a reasonably straightforward formulation of special relativity. Here's another version of the theory, which is called special relativity 2. By the way, this nomenclature is due to an excellent paper by Oliver Pooley, which I would highly recommend reading. I'm going to come back to Pooley's work a bit later in the talk. Here's the other version of special relativity. So instead of having a fixed Minkowski metric field eta, I have a dynamical metric field G, Lorentzian metric field. Now my dynamical equations are picked out by two equations, not only a massless Klein-Gordon equation where now I couple to G and use the derivative operator compatible with G, but I now have a second dynamical equation which says that this G, or the connection associated with this G, is flat. So now flatness of G is fixed dynamically by its own field equation rather than being fixed at the level of kinematics. So there's not much difference between these theories when one looks at the dynamically possible models, but they differ in their kinematical possibilities. So this guy can have curvature in the solutions which are kinematically possible models, but not dynamically possible models, whereas that's not allowed over here. Plausibly, we would like to say that both of these theories are background dependent, since we have something which is fixed in the dynamical possibilities. Okay, so that was the background. We can now move on to thinking about different definitions of background independence. So the first notion trades in terms of this idea of an absolute object. This is a notion which was initially articulated by J.L. Anderson in the 60s. The best source is the book that Tushar mentioned yesterday, Foundations of Space-Time Theories. Sorry, that was Michael Friedman's book.
Yeah,
Principles of Relativity Theory. So here's the idea of an absolute object, a geometrical object which is the same in all dynamically possible models of the theory. Now, this seems like it's going to give the right verdict on special relativity 1 and special relativity 2 because we have a metric field which is fixed in all of the dynamical possibilities of the theory. So there is an absolute object in both of these versions of the theory, so both of these versions of special relativity should count as background dependent. According to this definition, a theory is background independent if and only if it has no absolute objects in its formulation. Those versions of special relativity do have absolute objects, so they shouldn't count. Quite a nice idea. Unfortunately, this definition is going to be way too strict, and almost everything is going to violate it. The best source on this is a 2006 paper by our Cambridge colleague Brian Pitts. It's an excellent paper. He has a number of objections to this definition, but here is, I think, his master argument. General relativity has an absolute object. This absolute object is the square root of the metric determinant. It's a scalar density of non-zero weight because every neighborhood in every space-time model admits coordinates, at least locally, in which the components of the scalar density has a value of -1. So look, the square root of the metric determinant is something which is the same in all dynamical possibilities. So if I'm just using that definition of background independence in terms of absolute objects, even general relativity is going to violate this definition. So absolute objects can't be quite what we're after. And in fact, when you start looking at other space-time theories, it's not so hard to find absolute objects in all of them. So this definition is too strict.
Sorry, what? Why is this different than saying at one particular point I can find the metric coordinates in which the metric is Lorentzian? Why is it important that this can be done in a neighborhood rather than at a point? I could make the same argument and say now at every point I can, in ordinary GR, choose coordinates in which the metric has, the Lorentz form. The difference between this and the other one is can I do it point-wise? This needs to be done in an open neighborhood. Why is open neighborhood versus point-wise a determinant?
The point is that the metric determinant is the same in all solutions of the theory. I mean, you can evaluate it at a point, sure, but it's always going to be the same thing.
And the Minkowski metric,
Sure.
in
Sure.
normal coordinates is the same in every theory.
Agreed. So this, basically, the problem with this definition is that nothing's going to count as background independent because it's way too strict. People took a while to realize that, though.
But may I ask a simple question? Even not speaking about at time, this determinant is as different in the Cartesian coordinates in spherically symmetric ones. It's either +1 or r squared, the same theta.
But this number is always the same, right?
Well, why?
So I'm not disagreeing with you, but I think this still counts as something which is the same in all solutions. I mean, it doesn't matter the coordinate system in which you evaluate it.
When in which sense it is the absolute object?
Whatever coordinate system you choose, this guy's going to be the same. It's the same in all solutions of the theory, so it should count as an absolute object. Yeah. Anyway, we can come up with this. In fact, I think that there's more to this definition than we've said so far, so I'm going to kind of try and nuance it a bit later on, but before we do that, I'm going to go on to a completely different definition of background independence due to this guy, Oliver Pooley. So in his paper, which I mentioned a few minutes ago, he proposes trying to understand the idea of background independence in terms of variational principles. So here's what he says. A theory is background independent if and only if its solution space is determined by a generally covariant action, all of whose dependent variables are subject to Hamilton's principle, and all of whose dependent variables represent physical fields. GR is going to satisfy this definition. This is true of the Einstein-Hilbert action plus the matter terms that you might introduce. But special relativity 1 is going to violate this definition. When I think about the action for that theory, the Klein-Gordon action, this is going to have a fixed Minkowski metric field eta in it, which is not subject to Hamilton's principle. So this theory, good, is going to violate this definition. The question is whether SR2 satisfies or violates it. The first thing that we need to establish is whether SR2 has an action principle itself. In fact, it does. It's not too difficult to see what it would be once someone's written it down. This is due to Rosen. So all we do is we take this Klein-Gordon part and then we impose, using a Lagrange multiplier field, that the metric field should be flat. Now here, all dependent variables are subject to Hamilton's principle, so we might start worrying that special relativity 2 is going to violate this definition, sorry, is going to satisfy this definition and come out as background independent. In fact, that's the reason why here Pauli introduces this extra clause, all of whose dependent variables represent physical fields. The thought is that the physical status of this Lagrange multiplier field, theta, is highly dubious. We should regard it as being unphysical, and so by that second clause, special relativity 2 is going to violate this definition. Of course, this is already getting kind of murky because we need a criterion of what counts as physical. There are a few other worries about this definition. So there are other versions of special relativity. I can go to parameterized versions in which I write the metric in terms of these clock fields, which are dynamical. Plausibly, these are also physical because they're encoding the information in the Minkowski metric. Looks like those kinds of versions of special relativity are going to count as background independent according to this definition, which doesn't seem that happy an outcome. There's also this point that this definition assumes that every background independent theory admits of a Lagrangian formulation. You might want to leave open the possibility that you write down a theory which doesn't have an associated Lagrangian. If you think that that's a concern, then again you're not going to like this particular definition of background independence. Okay, so the third account, very nice account due to Gordon-Bellot. So this paper came out in General Relativity and Gravitation in 2011. It's quite sophisticated. I've kind of tried to simplify it. The main bit that I've cut out is this analysis of gauge redundancy. In fact, this isn't going to make too much of a difference in all of the cases that we're going to look at. Here's the idea. So I start off again with these models of a theory, these tuples. These O's could be either fixed fields or dynamical fields. I identify some of objects as representing geometrical structure. I just declare that. So here I've identified one of the O's as being geometrical, but you might identify more than one of them as being geometrical. Then you say that the geometrical degrees of freedom are the degrees of freedom needed to parameterize changes of these geometrical fields across dynamically possible models. So to anticipate, in that first version of special relativity, there are going to be no geometrical degrees of freedom because the Minkowski metric is the same in every solution. Physical degrees of freedom are then the degrees of freedom needed to parameterize changes of all of these O's across the dynamically possible models. So with that in mind, Bellot then gives a definition of background dependence and background independence, which essentially regard whether the number of geometrical degrees of freedom lines up with the number of physical degrees of freedom or whether there's a mismatch between them. So he says a field theory is fully background dependent if it has no geometrical degrees of freedom. Every solution is assigned the same space-time geometry as every other solution. So SR1 we can already see is going to count as background dependent according to Bellot. He says that a field theory is background independent, fully background independent, if all of its physical degrees of freedom correspond to geometrical degrees of freedom. So whenever I go to a different model, all of the physical stuff changes and all of the geometry changes. So the geometry is kind of covariant with the physical content of the theory. That seems to be what we're after when we're thinking about background independence. One of the good things about this is that Bellot's analysis allows for verdicts of intermediate degrees of background independence, where we have kind of, we can quantify the level of mismatch between geometrical and physical degrees of freedom. Did you have, I think there are a couple of questions. Yeah, I do.
Yeah, sorry, but according to this definition, if I have a theory like GR coupled to Maxwell, and then I constrain the Maxwell field to give just a constant electric field, that will still count as background independent? Sounds a bit weird. You just have a constant electric background, and you're not allowed to have any other configuration, but you will still call it background independent because what you fixed as an absolute structure is not a geometric object, or you're just counting geometric object any field?
I think this won't count as background independent because you're changing the geometry between models, but this matter, this electric field is fixed across models. So they're not appropriately covariant.
Okay, so in the definition, you're counting geometric every field, every tensor field of whatever type, including the Maxwell
Yeah.
vector field. Okay,
Yeah.
then I understand.
Sorry.
So I also have a related question. So it looks like according to this definition, classical GR is not background independent.
Yes. Yeah, I'm actually going to come on to this in the next slide. So I think these are both legitimate worries. In fact, Bellot kind of markets this as a virtue of his account that depending on the GR sector that you look at, you might not in fact regard it as being fully background independent. So just to say that GR is always background independent is too blasé.
I just have a finger on Daniel's question. Where the mic? So I have a finger. Without having specified the metric, what does it mean to have a constant electric field?
Sorry, I'm considering the case in which the space of solutions to the equation for the dynamical objects is trivial, at least for some of them. So you have Einstein-Maxwell, but then you constrain the variations, if you want, of the Maxwell field, so that in practice it is only one solution. In that case, I would call it a background-dependent theory because I'm basically fixing one of the entities in my field.
Yeah.
Although it's a geometric object that I'm fixing.
I think the concern that you're articulating is one that I agree with, and in fact I have a slide on it in about 3 slides time, so let's see if that addresses your concern.
Or you didn't mean constant through space-time, you meant constant through the solutions.
I'll move on, but we can discuss this if it's still a lingering issue. So first looking at SR1, SR2, the metric field is fixed in all DPMs, so there are no geometrical degrees of freedom. So these theories are background dependent for Bellot, so at least he gets the right verdict there. Now let's turn to general relativity. On the face of it, the thought would be that this theory is background independent because your matter is covariant with your geometry. Here's one example, actually an electromagnetic example as well, which might lead you to worry that it's not fully background independent. So consider Einstein-Maxwell theory. I can replace the Faraday tensor with the dual Faraday tensor, which will have the same stress-energy tensor. Then I seem to have different matter content associated with the same geometry. So that's not going to count as fully background independent for Bellot. I think the response here would just be this is actually fine. This sector of GR isn't fully background independent, it's slightly less than fully background independent. But that's a concern that you might articulate.
Well, without further matter, I think that's a gauge choice.
Not in anything to do with the standard U1 gauge symmetry of electromagnetism, though.
What? No, different type of gauge choice.
Yeah.
I mean, you could regard it as the same solution because you cannot distinguish between magnetic and
Yeah.
electric fields if you don't have matter.
Yeah.
To distinguish.
In fact, so this is one of the things that I kind of washed out. So the thing that I ignored in my analysis of Bellot was his analysis of gauge redundancy, just because it would have complicated things too much. If you want to regard these models as being the same, then maybe I'm supposed to say it's fully background dependent. Background independent, yeah. One moral that we're going to see with Bellot is that it's remarkably fine-tuned to subtle interpretative issues. Okay, so here are a couple of worries. So one worry is, consider this kind of gerrymandered theory. So I have kinematically possible models M, G, phi. In each of these models, these guys don't really do anything. They're not coupled in any interesting way. In every model, this adopts some inequivalent configuration, so they might not be diffeomorphic from model to model. And in every case, these are in 1-1 correspondence with configurations of this field phi, which are also inequivalent from model to model. So in this version, in this theory, it's going to count as background independent according to Bellot, even though these guys are not coupled, they're just inert in each model of the theory. So you might worry that Bellot's giving the wrong version here. Here's another worry, which is motivated from considerations regarding one version of Newtonian gravitation theory called the Newton-Cartan theory. So consider a theory with two fields which are designated as geometrical. One is dynamical, and one is non-dynamical. So G1 is fixed, G2 co-varies with this matter field phi. This theory is going to be background independent because geometrical degrees of freedom are co-varying with physical content.
I'm listening.
But we still have a fixed piece of structure in the theory. So this is, Bellot's account isn't kind of sufficiently attuned to the fact that you might introduce extra pieces of geometrical structure which are fixed. I guess the proposed fix is a fairly straightforward one, that you must say that each geometrical field has to differ between each non-gauge equivalent model. Good. So 2 more definitions, but it's not going to take too long to go through these. So I kind of want to return to the fixed field account. I feel like we might have written that off too quickly. So one thing that you could say is that a theory is background independent if and only if it has no formulation which features fixed fields. The thought would be then that special relativity 2 is just an equivalent form, or the same formulation as, or another formulation of special relativity, an alternative to special relativity 1. Since special relativity 2 has this alternative formulation which features fixed fields, it shouldn't count as background independent. So if we say that special relativity 2 is another formulation of special relativity 1, then according to this definition, we can say that those 2 theories are both background dependent. The main thing here is that it relies on some antecedent conception of theoretical equivalence. A lot of philosophers have been working on this, so I think there's a lot of different ways that you could fill it in. So Kevin and Jim in the audience, for example, could both deploy something like their definition of theoretical equivalence to fill the gap here. And I think potentially we can do a good job with this definition if we fill in the details in this way. And I quite like this because it's just more straightforward and less messy than the previous 2 that we've looked at. I guess there's an epistemological issue though. So how do we know that the theory in question has no formulation featuring fixed fields? In light of this, we can't just look at a theory and immediately adjudicate on whether it counts as background dependent or independent. The final definition in terms of absolute fields. So this is meant to be an idea somewhere between the notion of a fixed field and an absolute object. So they're basically the absolute objects which are explicitly written down in the kinematically possible models of the theory. So an absolute field is a geometrical object specified in the kinematically possible models, which is fixed in all dynamically possible models of that theory. So then we can say that a theory is background independent if and only if it has no absolute fields. SR1 and SR2 are both going to violate this definition because the metrics in those theories both count as absolute fields. But the idea is that we can avoid this concern about general relativity because the metric determinant wasn't one of the objects which I wrote down in my angle brackets, which specifies the kinematically possible models. Of course, this is kind of privileging quite strongly the stuff that I wrote down in the angle brackets, and you might think that that's somehow kind of physically unnatural. Okay, so I've got all of those definitions. Yeah.
What's wrong with looking instead just at the space of solutions of the classical equations of motion of the theory? You can, I mean, it would seem to me the most natural way of comparing 2 theories to just look at the space of solutions. Mm-hmm. If they are isomorphic, then they're the same theory and you're just comparing different formulations.
That sounds fine to me, so that would be one way of filling in a notion of theoretical equivalence in the penultimate definition. Oh, sorry. Yeah, one way of filling in the theoretical equivalence hole in the penultimate definition that I gave. In fact, that's not so far away from what Hooley articulates in his paper. Okay, so I've got those 5 definitions on the table. I'm just going to tell you the answers now. So here are 5 different classical space-time theories, or on the face of it different. So I have Newtonian gravitation theory, Newton-Cartan theory, a geometrized version of Newtonian gravitation theory, in which the gravitational potential is absorbed into the derivative operator of the theory. General relativity, teleparallel gravity, which is this kind of alternative version of general relativity in which I put my curvature degrees of freedom into torsion, and then a Kaluza-Klein theory. What comes out as what on these definitions? Well, good, Newtonian gravity consistently comes out as background dependent. Newton-Cartan theory more or less does, but Bellot's definition kind of gives the wrong answer. The reason being that some of the geometrical objects specifying geometry in Newton-Cartan theory are dynamical, but others are fixed. And that leads to the problem, the second of the two problems that I presented, where you have some pieces of the geometry co-varying with the matter content. But my proposed fix would turn this tick into a cross, so there's an easy way out of Bellot here. GR, aside from this bad no absolute object definition, consistently comes out of background. Independent, surprisingly though, so does teleparallel gravity. That's especially surprising considering that spacetime is flat in TPG, so flat spacetime doesn't always coincide with background independence. I can tell you a bit more about that if you're interested. Kaluza-Klein theory is also coming out as background independent for the most part. So insofar as you regard this as being a different theory to this, it's just not true to say that general relativity is the only theory which is background independent. Okay, I want to quickly go through how to extend those definitions to the quantum context. In fact, it's easier than you might think. And then we're going to look at quantum theories of gravity. I'm going to spend most of my time talking about string theory. So what would I do if I wanted to write down a quantum field theory in the angle brackety way that philosophers know and love? Well, when I'm thinking about, say, QED, I still use them in Cosmology, so I should presumably still have fixed fields there. But the dynamical stuff has to change. So these O's are now operator-valued fields. Now, dynamics is picked out not by dynamical classical equations, but by path integrals. So I could say that my dynamically possible models are then picked out by path integrals over these dynamical fields. I think that's the right way to understand quantum field theories in the philosopher-type way. We go. Well, let's talk about it.
I have a question. Why don't you use operator equations
Sorry, what do you mean by?
instead of saying path integrals?
Okay,
Why don't you say operator equations?
I shouldn't have said the right way. One reasonable way.
Okay, but I guess I'm a bit confused about what you mean by this criterion.
So what is?
When you say path integrals, you can write down this object, but what do you do with this object? So I'm confused what you mean by this.
Okay, so maybe I should add in some details. I guess I want to say that the dynamics is picked out by saying that there are certain correlation functions, and then I can use the path integrals to kind of compute the correlation functions.
But you haven't said anything about the ontology of your theory. This is supposed to allow you to compute some transition amplitudes or something like that.
Yeah.
Transition amplitudes
Yeah.
between what? Presumably between some particular state of affairs and some other state of affairs.
Yeah.
And in that state of affairs, the ontology of the theory should
Of course, there are
reside. So it's very strange to me.
ontological issues, but I guess this is just meant to be kind of trying to push quantum field theories into the same kind of mathematical presentation of KPMs, DPMs that philosophers have used in the context of classical theories. And that doesn't address all of the ontological questions for sure.
But I think, a very important aspect of the covariance or background independence should refer precisely about what the theory says there is in the world or not, which is in the ontology. So how can one discuss background independence without referring to what the theory says there is in the world?
Well, let's see what you think of the definitions as I apply them and see if you think they do a good job or not. Okay.
But
Yeah.
do you really mean, is there such an individual thing as a DPM in this picture? Or do you just mean we're going to say that any two theories that have the same set of path integrals have the same DPMs? I mean, so you put it up as the DPMs are literally picked out
Sorry,
by
what's
the...
DPM?
Dynamic possible models.
Is there such a thing as a model that, I mean, yeah, what is the model, what are the models? Yeah.
Part of the problem is there's no propositional content in the second bullet point. Like there's no like equal sign or
Yeah.
this is Robert's point. Like
Oh, I
how do
see.
you distinguish one that is and is not?
Right, yeah, you're right. So I think I should have had like an extra line about, we want our DPMs to be such that the correlation functions are such and the path integral picks out these guys.
That makes more sense to me.
Okay.
So what's I mean, I know what a classical DPM looks like. It's some particular, value of the different geometrical objects on a manifold. What is
Yeah.
it? What actually is formally a DPM in this case?
I specify operator value fields. I mean, basically what I just said to Jim. Did that not? Oh, sorry. Was what I said to Jim not sufficient?
So doesn't there have to be so you mean particular, okay, so particular sort of Heisenberg operators, something like that,
I think there's a few different ways that you can package
for
this.
some particular state or something.
I mean, I'm kind of being blasé and quick here because actually it doesn't matter too much for what I'm going to say. So I propose to return to this in the questions because this isn't going to be super important for translating the definitions of background independence to the quantum context. Essentially, in virtue of the fact that it has some fixed fields there, so I can just straightforwardly move a lot of the definitions over. Let's come back to this. So, in fact, all of the definitions except the one in terms of variational principles seem to carry over pretty straightforwardly. So, just think about the one that says the theory has no formulation in terms of fixed fields. That seems to be totally fine in the quantum context as well. The only one which seems to need significant modification is the variational principle one. I also want to take into account the path integral measure. So it seems natural to say something like this. A quantum theory is background independent if and only if its solution space is determined by a generally covariant path integral, all of whose dependent variables are integrated over in the path integral, and all of whose dependent variables represent physical fields. Something like that. Okay. Let's now think about strings. So here's a quick presentation of string theory. Obviously, there are a number of people in the room that know more about this than me, but I think this is sufficient to get the points across. So in string theory, a string can be regarded as a special case of a p-brane, which is an object with p-spatial dimensions in tension Tp. The classical motion of a p-brane extremizes this p plus one dimensional volume that it sweeps out in a space that we're not going to yet call space-time, but we're going to call some target space. So the p-brane action will generally look like this. If p is equal to 1, then this action becomes this guy, the so-called Nambu-Goto action. These x's describe the embedding of the string in the target space. This is the Minkowski metric on the target space, and these sigmas are coordinates on the string world sheet. It's actually quite difficult to work with that Nambu-Goto action though, so we can write it in another way by introducing this field h on the string world sheet, and then I can write this action as this guy, the Polyakov integral, Polyakov action. I can recover the Nambu-Goto action by varying with respect to h and then eliminating it using its equations of motion. Now I can quantize this guy and define operators, ladder operators, to study the spectrum of the string. And if I look at the first excited state, I find that there are 3 first excited states. A symmetric rank 2 state, suggestively known as the graviton, an antisymmetric state, the B field, and this scalar field, the dilaton. Now a move happens in a lot of string theory textbooks which comes very quickly and which has aroused the interest of a number of philosophers, including Nick Huggett, who's with us today. So we move from treating looking at those first excited states of one string to those states being classical background fields on the target space in this kind of enriched Polyakov integral. Now you might think that that's really quick, kind of what are the missing steps there? Well, it's something like the following. I'm to envisage a number of strings distributed across target space, all of which are in, say, the F excited state. And then if I kind of ignore both stringy and quantum effects, then these start looking like background fields on the target space. Clearly there's a lot more to say there. So Nick in particular has kind of tried to articulate what's going on here in terms of the machinery of coherent states, a way of kind of recovering classical objects from quantum mechanics. But what we need to recognize is that this guy is to be understood as ultimately composed of strings. It's a field on the target space, but it's not a fundamental object. It's kind of ontologically reduced to a coherent state of strings. So now I have on the target space not just this field eta, which is ontologically primitive, but also this f, this b, and this phi, which are composed of strings in some sense, which deserves and needs to be made more explicit.
Sorry, at the classical level, then I'm talking now about a huge collection of strings propagating in this background spacetime, and therefore giving. But for it to be defined at every point in the background spacetime, it should be filling. The whole thing should be filled with these things.
Agreed. That's something like the picture that we have in mind. A couple more things to say here. So it turns out that in string theory, this H on the world sheet has to be conformally invariant to cancel an anomaly, and so in order to have a well-defined theory. Now, if I'm looking at this action, I can read it also as an action for a 2D quantum field theory, where the fields are these x's, and I have this metric field H. If I have that reading of this, then these guys are coupling parameters. So I can compute the associated beta function to see how they run with energy. And then the string theory calculation is, once I've computed these guys, I can set these beta functions to vanish, given conformal invariance of the string world sheet.
And when you talk about energy, you talk about the energy that is inferred from the metric background that you put at the beginning. That's what defines energy, presumably, and actually in some particular frame or something like that.
Well,
so what is energy?
The relevant metric is now this H, because we're looking at 2D QFT. We're kind of reading this as a 2D QFT, but these are coupling parameters. So if we run this analysis...
But nevertheless, running is, even with that metric, to define energy, you have to tell me a particular killing field or observer field or something like that that you will use to define the energy of the particular excitation.
You could do this using H.
But it's not enough. It's not enough using H. I cannot tell you what the energy is in Minkowski spacetime until you give me which frame you're talking about.
You don't need to.
The
conformal symmetry is with respect to H on the world sheet. You treat it as a space-time. That's the symmetry.
No, I'm talking about something very simple. The notion of energy in special relativity depends on the observer. In GR depends on the even stronger, right?
We're not doing GR now.
In any space-time, when you say the word energy, you refer to certain, you can define an energy momentum tensor, but you cannot define a value of energy until you tell me which observer you are going to assign this energy to.
Okay, so should I just have said compute the beta functions associated with these coupling parameters?
Okay, running with what?
What?
I mean, beta functions are running with something.
Yeah.
And running with what? What is the running parameter on which these beta functions?
Well, I would say energy as associated with this guy, but...
And with this guy, I'm an observer. I'm a particular frame.
I'm not really following this.
I have a particle in world space-time, in Minkowski space-time. What's this energy? You cannot tell me what this energy is until you tell me which observer you refer to.
Well, it's associated with a certain killing vector field, though.
Sorry?
It's associated with a certain killing vector field.
But which one?
I think this is aside from the main
Yeah, let's
point
return
here.
to this again. I'm sorry, but we can talk about it more. So if you do this, and then you set the beta functions to 0, string theorists claim to be able to find that those background fields satisfy the Einstein equations plus some dynamical equations for matter fields. Where this guy, this big G, is now the metric field. The Einstein tensor associated with this composite metric field consisting of eta and f. So just to emphasize something that I've already said, this metric field G is composed of this fundamental metric field eta plus this F, which is meant in some sense to be composed of strings. So it kind of has two components which have, on this picture, different ontological statuses. One is primitive, one is a composite object. Can we understand this guy to also be composed of strings? Well, not straightforwardly, because this guy has a trace. The graviton excitations were trace-free. Nick and I have corresponded about this a bit, but there doesn't seem to be any easy way to get rid of that Minkowski metric to understand it as also being composed of strings. Okay, so now let's assess the background independence of this theory. In fact, there's a few different ways you can go. So there are three main possibilities. The first is that you look at the target space fields but think about just G. The second is you look at the target space fields but think about eta and F. And the third is that you look at the world sheet fields, so H and X's. And we'll get different verdicts in each of these cases. So let's start off with just looking at the background fields G, B, and phi, understood now as classical background fields which satisfied those equations on the previous slide. Well, if I'm looking at this guy, there are no fixed fields and no absolute fields. There is still an absolute object, this square root of the metric determinant. The dynamics of these fields can be derived from their own generally covariant action. So that definition of background independence would seem to be satisfied. And Bellot's definition would also seem to be satisfied. So if I'm thinking about string theory in this way, then there's a good case to say that it is background independent. And I claim that this is the way that, for example, Huggett and Vistorini are thinking about it in their philosophy of science paper. They're looking at G's and B's and phi's on the target space, having run this analysis which I just ran through. That's not the only way that you could go, though. So you could also think that the relevant target space objects aren't G, but the more fundamental, in some sense, eta and this composite object F. Well, now you get a totally different verdict. So now you do have a fixed field, this guy, absolute field, absolute object, and variational principles are also violated because this guy is not subject to Hamilton's principle. The only case which is a bit subtle here is Bellot's definition. Even though eta is fixed, F is still geometrical and dynamical, and it seems to be covariant with the other matter content of the theory. So kind of like that Newton-Cartan case which I presented a while ago, Bellot's definition would give the verdict that this is in fact background independent. The other thing that you can do in strings is to look at the world sheet fields. So now we're looking at H and X. Both of these are variational, and they're not fixed. There is still an absolute object to this guy. You might think that these guys are fixed, but on the world sheet interpretation, they're actually viewed as function of the X's. So those objects aren't fixed either. You might worry that these X's are violating a prohibition on unphysical fields, but that's not obviously so since they're encoding the string's position or location in target space. Whether you view H as physical depends upon whether you view it as a fundamental field or an auxiliary construction. But remember that I introduced the Polyakov integral saying that this was just an auxiliary field. On that sense, it's not obviously physical, so that's really the thing on which the variational principle definition hinges. On Bellot's account, it's natural to construe this H as being the geometrical structure of the theory. That's the geometrical structure on the string world sheet. But it's possible to eliminate that from the Polyakov action, right? So potentially I can envisage different H's, but the same X's. And in that case, Bellot's account is not going to say that the theory is fully background independent, because I could have different geometries but the same physical content of the theory. So overall what I get is this table in the context of string theory. So the theory broadly comes out as background independent if I'm looking at the G field on target space. Broadly comes out as not background independent if I'm looking at the eta field on target space. I think this is the main difference between the Ravelli-Smolin reading on the second line and the kind of Huggett-Vistorini reading on the first line. If you start looking at the fields on the string world sheet, it's really quite messy to get a clear verdict on what's going on. Some accounts say that the theory is background dependent, others say that the theory is background independent. But in any case, I hope it's clear that this is a much more subtle and nuanced picture than just saying string theory is transparently background dependent or something like that. It really depends on the definition you're using and which bits of the theory that you're looking at. Loop quantum gravity, I just have a single line, a single slide. But in brief, if we apply these definitions to quantum gravity, we find that the theory is background independent. So I have no quibbles with the Ravelli-Smolin claims there. So let me just summarize. So I've done a few things today. I've presented 5 definitions of classical background independence. I've claimed that GR isn't privileged with respect to its satisfaction of these definitions. I've tried to extend these to quantum theories, and I've assessed the background independence of string theory, and I found it's more subtle than you might think. Thanks very much.
In connection with something I mentioned before, it's very important that these things that we give geometrical names play the geometrical roles they are supposed to have. And in particular, in a quantum theory, when we do, standard type quantization and try to construct the quantum fields, one thing we do is construct permutation relations that are constrained by the causal structure of the theory. It's very difficult to envision, I'm not an expert on, but how the presence or not of these graviton fields could change the causal structure so that the thing that you now call the metric, which is this composite object, would in fact provide the kind of constraint that we use when we say, quantum field operators should commute at space-like separations given by that correspond to the ones given by the metric. So it's not clear to me not only how this move occur of things filling space-time, but even in the quantum sector, it's very difficult to understand how this thing we are now giving the name, the metric of space-time, could play that role that the metric is supposed to be.
I more or less agree with you. So all of the quantization machinery in standard string theory proceeds using eta. We end up building this G. But what you just said is kind of a motivation to look at the second line rather than the first line of that table, which I had a few slides ago, to think that really the relevant object is still eta.
Okay, then we have a problem.
Then on that way of understanding things, the theory is, on most accounts, background dependent. I think there was maybe a finger on this over there.
Yes. This is. I'd just like to take this chance to advocate my own work. I recently proposed an approach to quantum gravity called world quantum gravity, and it incorporates superposition of causal structure, as Daniel pointed out. It is expected to have, or maybe. So the basic idea of the approach is that if you have a background independent theory, according to your definition, you do the path integral, you sum over all the configurations, all the fields, including the gravitational configurations, then you would expect to have gravitational configurations of different causal structures, and you would have them in superpositions, you have indefiniteness in causal structure. And in this approach I proposed last year, I did incorporate this feature.
Thanks. I'll definitely have a look.
David? I fully agree with your assessment that string theory qualifies as background independence based on your criteria, but I think one should read Smolin and Ravelli to make a more methodological point, not aiming at characterizing the full theory, but characterizing the approach starting from a perturbative starting point, and just making the point that in that process that might or might not eventually lead to a fully fleshed out string theory, the theory is not manifestly background independent as one goes on step by step. So I feel that would be a different kind of claim than the one you discuss in your presentation. Would you agree to that?
So first on the claim that string theory is background independent, I guess to repeat, it is a function of what you're looking at. So just like the interaction with Professor Zadarsky. So I don't necessarily want to say it is background independent. I want to say like there's more. You need to say more before this is a meaningful thing to say. When it comes to the claim that the main issue with string theory is that it starts from a perturbative starting point, I also understand that, and I agree with that claim. I guess I don't agree with the claim that it is manifestly background dependent. In fact, to be honest, don't really like this talk of manifest background dependence or independence, because things aren't really manifest to me until I define what I'm talking about. I guess this was a kind of project in trying to make things more manifest to myself.
It was far too similar to Richard, so since we're running low of time, I'll start on the queue.
Thanks. Initially, you presented this as, the big question is what's the central innovation of GR? It's background independence. And then one of your conclusions is, well, but GR isn't privileged in that sense because there are all these other theories which are, at least according to some of these reasonable definitions, background independent. That is true, but I think that's still consistent with the possibility that it's the central innovation of GR, that this background dependence, because in the development of theories of gravitation, it was the first one where this was really explicitly becoming a central important feature. So it's an innovation that may then have later been copied by other theories. And in that sense, the original claim might still be true, no?
So you're saying it's an innovation. What is the reference of it? Which?
The background independence of GR.
But what is which? Just which notion? I guess that's part of that.
You mean which definition?
Yeah.
Oh.
So I think that
if you would bring up the slide with the appraisal of GR, or the classical theories, I should say, you see that it comes out as background independent on most of them, if I remember correctly. There were some asterisks in there, which I'm not sure what exactly they were.
the asterisks mean things are subtle in various ways.
Okay, subtle. There may be some subtleties, but largely you said, it comes out as background independent, forgetting about the first notion. And it's not unique in that, because there are at least these two other candidates which are also background independent in more or less the same way. While that is true, it may still be the case that it was its innovation of being the first theory that was background independent in number 2 through 5.
I mean that is true that. Not focusing on any one particular definition, there's a transparent difference between Newtonian theories and general relativity when you look at this slide. And so you could say that GR is innovative in the sense that it manifests all of these things that didn't come before.
Yes.
That seems totally fine to me. But I think we can get misled by thinking that there's one thing which is special about general relativity which we need to identify. There are loads of different interesting features which it shares or doesn't share with theories which came before, and I think it's better to kind of supervaluate over all of them.
Okay, first I want to repeat what I said with the statement that the determinant is absolute. I don't quite understand it. So what we know from the standard relativity, if we took the Einstein action and make variation for all metric and make exploration for all metric compounds, but still considering in that sense that determinant is an absolute quantity, so you're not trying it. It's well known what is obtained by so-called unimodular theory of gravity, which is independent from the Einstein one. It's Einstein gravity plus and arbitrary cosmological term which is an integration constant. But once more, it seems that this is different from what you said. And my second question, you introduced this definition of below the definition of background independence. Once more, my question is because once more I have to admit that I never heard about it. What would be bad if this definition is not satisfied? Are there any new observable effects like those which were well known in general relativity as test of the absence of the preferred inertial frame and so on?
Well, if let's look at to focus on your second question first. Let's look at the point that I made with Belot about this, the electromagnetic duality in Einstein-Maxwell theory. You could say, in light of the fact that it seems like this sector of general relativity is not fully background independent, that's kind of flagging some important interpretative issue, that in fact these should be regarded as gauge equivalent models, and that the difference between these models, at least in this case, is not an observable difference. So it might be a useful guide to the interpretation of particular sectors of GR. But there's no super straightforward connection between empirical content and whether background independence or dependence is satisfied. When it comes to the point about the metric determinants, so, I mean, it is just true that this is the same in all solutions in all dynamically possible models of general relativity. But yeah, I feel like I might not be fully understanding your question here, so we should definitely talk about it.
What's more, my question is the relation for the standard so-called unimodular equality, in which indeed the determinant is not right.
Yeah, thanks. Sorry, I missed that. So yeah, in fact, Pitz's paper was motivated by first looking at unimodular gravity, and he says, oh, there's transparently an absolute object in unimodular gravity. But in fact, once I've noticed this in unimodular gravity, I can just apply the same kind of reasoning to GR as well.
I apologize to those who still have questions, but we have to stop. So I invite you to discuss over the break. Let's thank our speaker.